So we have other methods of solving first order and first degree ordinary differential equations. So we have inexact differential equation. So if the partial derivative of m with respect to y is not equal to the partial derivative of n with respect to x, then it is an inexactly. So we introduce what we call an integrating factor to transform the inexact DE into an exact DE. So it's a function multiplied to an inexact differential equation to again transform it so that it becomes an exact differential equation. So here's what we do. We multiply the entire equation by the integrating factor, and therefore the partial derivative of the new expression with respect to y, the new expression b, k integrating factor multiplied to m is now equal to the partial derivative of the integrating factor times n, k with respect to x. So depending on which of the following conditions are applicable. So if this expression is a pure function of x, then we let the integrating factor be equal to the e raised to the integral of f of x dx. And if this expression is a pure y function, then this is the corresponding integrating factor. And if v is a function of both x and y, so it's not pure x, it's not pure y, then we use this definition where m and n are determined from this equation. So we solve for this value and then compare it with this value. So the m and n functions are, or rather the numbers, okay, not just functions, they are specifically numbers. They are the exponents to x and y respectively. So here are the steps to solve an inexact differential equation. So we first test for exactness. If proven inexact, then solve for the integrating factor and then multiply the integrating factor to the inexact differential equation and then test again for exactness. And once proven that it is already exact, then solve it as an exact differential equation. So let's have an example. So for this one, in the x term, so we label that expression as x, or rather m. So we let m be 3xy squared minus 4y, and let n be 2x squared y minus 2x. So we are going to test for exactness. Is the partial derivative of m with respect to y equal to partial derivative m n with respect to x? So this partial derivative with respect to y for 3xy squared minus 4y. So this is just for discussion purposes. You can, of course, just give the derivative right away. Okay, so for this one, it's derivative of um 3xy squared with respect to y. Okay, y is the variable, so it's 2y for the derivative of y squared times the constant, which is 3x. So it's 6xy, okay, for the first term. And then for the second term, that's pure y, so it's minus 4. For the right side of the equation, so we are going to partially differentiate n, okay, which is 2x squared y minus 2x. With respect to x, so y is the constant. All right, so for 2x squared y, so derivative of x is 2x. Multiply it to 2y, the constant, so that's 4xy. And then for the second term, that's minus 2. Okay, so obviously, the left side is not equal to the right side. Therefore, okay, it is an inexact DE. So I'll just write IDE. Okay, so the second step is to solve for the integrating factor. So we're going to try if we'll get a pure f of x if we are going to multiply 1 over n by this expression. Okay, so what I usually memorize is if it's f here of x, then it's n here. If it's n here, then for the first expression, so it's going to be m and then n. So let's see if it's pure f of x. So n is 2x squared y minus 2x. So for the first expression, it's from step number 1. It's um, 6xy minus 4, and then minus 4xy minus 2, 4xy minus 2, or it's quantity 4xy minus 2, so minus 4xy plus 2, right? So let's see if we can get a pure function of x. So if we're going to factor out the greatest common factor for the denominator, so it's 2x, so we get xy minus 1. Okay. And then for this above, okay, so it's 2xy, so let's write the result here, 2xy. Combining like terms, we get 2xy and then minus 2. So we're going to factor out um, 2 for the greatest common factor. And then we have xy minus 1. So we have the same factor and this also 2. Therefore, the right side is 1 over x. So it's a pure function of x. Okay. So therefore, we are going to use v. Okay. The integrating factor is e to the integral of f of x dx. So it's e to the integral of 1 over x dx. And integral of 1 over x dx, it's ln of x. And e to the ln of x, okay? Using one of the properties of logarithm is always equal to x. So we'll use this integrating factor. So just to check, okay, if the other test, okay, other way of proving if the integrating factor is pure x or pure y. So let's check if this would result to a non-pure function of y. So if it's g here, then it's m in the denominator, and for the expression inside the parentheses, so it starts with n and then followed by m, right? So is it 1 over 3xy squared minus 4y? You can simultaneously perform this operations and then factoring out the greatest common factor para one step lang in the solution. Okay, this is again for discussion purposes, so that's why it's complete. So partial derivative of n with respect to y, that's with respect to x rather, it's for xy minus 2. So for xy minus 2, minus quantity 3x squared, or rather 6xy minus 4. So that's 6xy plus 4. Okay, so we're going to factor out y here in the denominator. So we'll have 3xy minus 4 for the second factor. And for this, combine like terms, it's negative 2xy plus 2, right? So if we're going to factor out 2, so it's negative y, okay, or xy rather, and then plus 1. So we do not have a common factor that we can cancel out. And obviously, so this contains x and y, x and y. Just not pure y for the expression. So therefore, k is not equal to this. It's not a pure function of y. Therefore, we do not base k, the integrating factor, from a function of y. Okay, instead it should be a function of x. So specifically x. So step 3 is we're going to multiply the whole equation by this. So step 3 is we're going to multiply the whole equation by x. So we're going to multiply that by x. Okay. So let me write first. So we're going to multiply each term here by x. And for the second term, the dy term, so it should also be multiplied by x. And right side is still 0. We're going to distribute, so it's the x squared y squared minus 4xy dx. And then we have 2x cubed y minus 2x squared, or the dy term equals 0. So we're going to test for exactness again. This time, we expect that it is now an exact differential equation. Okay, so check if this is true. Okay, so the new m, okay, or basically that's v times m. So if we're going to retain the original letters, okay, so it's v times m, or you can just label it as m, okay, as long as you know that it is the new m rather, and also the new m. So this should be v times n. Okay. So is the partial derivative with respect to y of 3x squared y squared minus 4xy equal to partial derivative with respect to x of 2x cubed y minus 2x squared. So for the left side, x is the constant. So derivative of y squared is 2y times 2x squared. So that's 6x squared y minus 4x for the second term. And on the right side, so we have x for the variable. So derivative of x cubed is 2x squared. So times 2y. So it's 6x squared y. And for the second term, that's 4x. All right, so the left side is equal to the right side, therefore it is an exact differential equation. So we solve it as a differential equation. That's for the next step. Okay, so um, for exact DE, so recall, okay, so we have identified the new M and N already. So what we're going to do next is to choose between the two. Okay, which would be our basis. So, so if I am going to choose um, the dx term as the basis, so we are going to solve for f, okay, and then we're going to integrate the dx term, right? Sorry, and the new dx term. Okay, so it should be this new equation. So we can label it. Okay, so this part, it's already exactly. So it should be the new dx term. So it's going to be 3x squared y squared minus 4xy dx. Okay, the integral of this partially, okay, integrating with respect to x. Change the notations. It should be partially with or partial differential of x. Okay, so we simply copy the new term and then integrating partially. Okay, so y here is the constant. So integral of x squared is x cubed over 3 times 3. So that's x cubed. And then the constant, which is y squared. So that's x cubed y squared. And for the second term, that's integral of x. It's just 1. Okay, and then, no, it's not 1. Sorry, it's x squared over 2. Sorry, times 4y, a constant. So it's 4x squared y over 2, or that's 2x squared y. Okay, and then for the constant, arbitrary constant, or the constant of integration, so y is the constant, so we use g of y. So we need to solve for the value of g of y. Okay, first we need to solve for the partial derivative of f. Okay, with respect to y this time, not with respect to x. Okay, so x is the constant. So it's 2y, or rather, yeah, 2y for the derivative of y squared, and then times x cubed. So that's 2x cubed y. Okay, am I correct? So it's 2x cubed y. And then for the second term, so that's derivative of 2x squared y, so it's 2x squared. And derivative of g of y is g prime of y. Okay, and this partial derivative of f with respect to y is actually the n. Okay, in the first or the second, rather, the new equation. So this is going to be equated to n. Okay, so n, the new n here, it's 2x cubed y minus 2x squared, and on the right side, so we copy this. So it's 2x cubed y minus 2x squared plus g prime y. So actually, I'm going to eliminate these and also these. So we're left with 0 for the g prime of y. So don't fret. Okay, so we integrate. So that's g prime or g of y, therefore, is a constant. Because the derivative of a constant is 0. So integral of 0 is a constant. So we're going to plug in that into the one with the g prime of y equation. So this equations, we can maybe put some indicator here as a star, or label it as equation 1, whatever. It's up to you. Okay, so we're going to equate this f. Okay, so the solution, no? Therefore, is x cubed, okay, x cubed y squared minus 2x squared y, and then plus g of y, okay, which is c, and equated to another constant. So the combination of the two terms is still a constant. So therefore, we have x cubed y squared plus 2x y, okay, equals c. And using the conditions here, x equals 1 and y equals 3, so for c. So it's 1 for x, and then cubed, and then 3 for y, so 3 squared minus 2 times 1 squared times 3, okay, is c. So that's 9 minus 6, okay, so it's 3. So the c value is 3. So we're going to plug it into this equation here, okay, or rather here in there. Where is it? Okay. So if we're going to plug in the value of c, sandali na to ito pa. Okay. So the value of f is going to be equated 0 for the what do you call this? Sani. So anyway, so um the value here of f is x cubed y squared is 2x squared y, okay, plus g of y, which is a constant. Okay. Just basically, this is the value of f, okay, and then we'll just replace the value of c with 3. So it is from this equation, right, this is x squared, or rather x cubed. It's x cubed y squared minus 2x squared y. Okay, and then the c is 3. Okay, so we're combining, by the way, the two c's. So it should be referring to this equation here and not that equation. So therefore, the final answer is x cubed y squared minus 2x squared y equals 3. So this is the solution to the given differential equation. So here's another example. So we're going to first distribute y. So it becomes 4xy plus y squared for the dx term, and 2y minus 2x squared for the dy term. Okay, so we let the dx term be the m and the dy term be the n. So we're going to test first if it's exact or not. So it's 4xy plus y squared with respect to y differentiation. Okay, partial derivative is the constant here is x. So it's 4x, okay, plus 2y, and for n partial derivative with respect to x. Or you can do the one with the equation, proving if left side is equal to the right side. Okay, or tagsa-tagsa, no? Na solve for these two. So the y here is the constant, so it's 0 for the first term and for x for the second term. Okay, so since the two are not equal, right? Okay, therefore this is an inexact differential equation. So next step would be to determine what is the integrating factor. So or no, not that yet. So we're going to see if this expression on the right side is equal to an f of x, a pure function of x. Okay, so if it's already n here, then the one inside the parentheses should start with m and then n. So it's n is 2y minus 2x squared. So you can write n, and then since we're going to see if it's pure x or pure y, so um, let's factor out. Okay, this common para dili na daga isulat, no? So for 2y minus 2x squared, and so common factor is 2. So that's y minus x squared. Okay, and then for here, that's 4x plus 2y, then minus negative 4x, or that's plus 4x. So we can also combine similar terms. This is equal to 8x plus 2y. So greatest common factor is 2. Okay, let's factor that out. And then 4 plus y. Okay, inside. Okay, the second parenthesis. So obviously, there's two only common factor that we can cancel out. So it's not a pure function of x. Okay, so not a pure function of x. Here you can put here. So we go to the next one. Okay, so to see if this 1 over m times this is a pure function of y. So m is 4xy plus y squared. So common factor is y. So it's 4x plus y. And then times negative 4x. Okay, minus quantity 4x was 2y. So meaning minus 4x minus 2y. Or that is negative 8x. Okay, minus 2y. So we can put negative 2 here. So meaning it's 4x plus y, okay, for the second factor. So for this one, we have 4x plus y, the common factor. Okay, so what is left on the right side is a pure function of y. Okay, so it's 2 in the numerator and then y in the denominator. Okay, so it is a pure y function. Therefore, we let the integrating factor be equal to e raised to the power of the integral of g of y dy, okay, meaning e raised to the power of the integral of negative 2 over y dy, or that's e to the negative ln of y, okay, or that is equal to e raised to the power of ln of y raised to the negative 1, okay, or sorry, forgot to put the 2, so there's 2 here, and this is negative 2, not negative 1. Okay, therefore v is y raised to the power of negative 2. So the integrating factor that we're going to use is y raised to the power of negative 2. So step 3 is we're going to multiply the whole equation by the integrating factor, y to the negative 2. So there's step 3. So for xy times y to the negative 2, so that's 4xy to the negative 1. And then y to the power of 2 times y to the power of negative 2, that's y to the 0 or just 1. And then for the second term, so that's 2y to the negative 1 minus 2x squared y to the negative 2. Okay, dy. So this should be dy. Okay, and then equals 0. So we now have a new m. So it's v times the original m, or we use na lang the same letter. Okay, so the new m that we're going to test later if it's exact na ba na differential equation. This one. And n is 2y to the negative 1 minus 2x squared y to the negative 2. So next step would be to test again for exactness. So this time we expect that it will yield, okay, an exact b. So we partially differentiate this m with respect to y. So x is the constant. So it's 4x times derivative of y to the negative 1. It's negative y, not raised from negative 2. And then it's 0 for derivative of 1. So this is negative 4xy to the negative 2. Okay. And for the n, we partially differentiate this with respect to x. The y is the constant. It's 0 for the first term, and then that's minus 2y to the negative 2, okay, times 1. Okay. So this is supposed to be squared. So nalili ma-equal. Okay. So this should be multiplied, the constant will be multiplied by derivative of x squared, which is 2x. So it's negative 4xy raised to the power of negative 2. So since the two are equal, then this is already an exact differential equation. So we're going to select, okay, which between the two, the new m and n, okay, by the way, ito ang basis for solving for f. Let's say I'll choose dx since the dx term, since the second term is just, okay, the second, yeah, term in this expression is just 1, and it's not complicated, like any daghan exponents. Okay. So if you want to use n, then go ahead, no problem. Okay, so that's 4xy to the negative 1 plus 1. We partially integrate this, okay, with respect to x. So y is the constant. So it's 4y to the negative 1, the constant, multiplied by derivative or integral of x rather, which is x squared over 2. And then for 1 dx, its integral is x, and then the constant, okay, of integration is pure function of y, or g of y. So this is Bale, 2x squared y to the negative 1 plus x plus g of y. And we are going to get back, okay, to this equation. So we can um, put an indicator, okay, or label this equation 1, or underline it maybe, or box it. Okay, we need to solve for g of y. So that and equate this f not to c, and that would be the solution to the dE. So next step is to differentiate partially with respect to y. Okay, so meaning that's 2x squared times derivative of y to the negative 1. It's negative y to the negative 2. Okay, and then 0 for the second term because x here is the constant. And then g prime of y, okay, for the derivative of g of y, or that's negative 2x squared y to the negative 2 plus g prime of y. And this is equal to n. So we plug in the value of n. Okay. So a common term on both sides of the equations. We can cancel these out. So leaving a g prime of y, okay, which is a pure y, okay, na 2y to the negative 1. And by integration, we solve for g of y, okay, so the integral of 2y to the negative 1, okay, with y as the variable of integration, is 2 ln of y, right? This is 2 over y, so 2 ln of y. All right, so we are going to go back to this equation. Okay, this equation here. So we are going to equate um, that later to see for the final answer. So copying it and replacing g of y with 2 ln of y. So equating this to c plus 2 ln of y equals c. Okay, or maybe in some books, okay, they don't put an expression with a negative exponent. So we're going to multiply the whole equation by y, okay, to remove this y to the negative 1. So meaning that's y to the 0. Okay, so if we're going to multiply the whole equation by y, the purpose again is to get rid of that negative exponent. So it's 2x squared y to the 0, or that's 1, okay, for the first term, and then xy for the second term. And then it's 2y ln y, okay, equals cy. So the answer is 2x squared plus xy plus 2y ln y equals cy. Okay, or you can also use this as your final answer. But if it's required that the exponent should be positive, then you should write this one. All right. So for this next example, this is not yet written in differential form. So let's transform this first. Okay, so let's write this as dy dx. And then going to determine what's the dx term and the dy term. So by cross multiplication, so it's x times x squared y cubed minus 1 multiplied to the dy term, or the dy rather, and the right side it's 2y dx. And if we're going to arrange terms, start with dx and then transfer the dy term to the other side, okay, and then 0 on the right side. So let's multiply first x to x squared y cubed minus 1. So that would be x cubed y cubed minus x. Okay, because 0, or if you want to distribute the negative sign, Okay, from here that okay, put na. So we are going to label 2y as Rm and n would be negative, or again, if you want to distribute the negative sign, pwede po. So we're going to test if this is exact or not. So m with respect to y, okay, so that's 2. And then for n, differentiate it with respect to x. So y here is the constant. Okay, for the first term, so that's negative 3x squared y cubed. And for the second term, it's plus x. Okay, so meaning plus 1. All right. Or you can put the negative sign first, and then find the derivative of these two. Okay, not necessarily now you have to distribute the negative sign. So obviously, the two are not equal, so it's an inexact differential equation. So this is step number 1. Okay. And then step number 2 is to determine what's the integrating factor. So we are going to see first if this 1 over n, okay, times this is a pure function of x. So it's 1 over negative of x cubed y cubed minus x. Okay, times 2y minus n, or rather, sorry, that's m, should be 2, and then minus quantity this, meaning that's plus 3x squared y cubed minus 1. Okay, if we're going to be factoring out the GCF, so it's x for the 1 here, the denominator, so that's x squared y cubed minus 1. And then here, there's no common factor, so just combine 2 and minus 1. So that's 1 plus 3x squared y cubed. Or if you can see na it's really not a function of x, okay? Even if you haven't factored out the expressions completely, naklaro na it's not a pure function of x, then you can stop there and then try the other part. So is 1 over m times this. Okay, a pure function of y. So 1 over m is 2y, and then this one is negative 3x cubed. Okay, sorry, 3x squared y cubed plus 1 minus 2. That's 1 over 2y, and then we have here, okay, no common factor here also, so it's only 1 minus 2, or that's minus 1. So this is also not a pure function of y, so therefore um, the integrating factor would be the one with both x and y, x raised power of m and y raised power of n, and we need to solve for the values of m and n. So we're going to copy this expression from the solution above and equate it to the m times n over x minus n times m over y. Okay, so this expression is basically this. Kani simplified, kani. So that's 1 plus 3x squared y cubed, and then m, the unknown, k, times n, which is negative of x cubed y cubed minus x, or that's negative x cubed y cubed plus x. Okay, divide this by x. And for the second term, it's n times m is 2y over y. So that's m times each term divided by x. So that's negative x squared y cubed. If I'm going to distribute already the negative sign, so negative of negative x is positive x or plus x over x. So that's plus 1, right? And then that's minus cancel the y's. So that's 2n for the second term. We're going to equate this. Okay, so if we distribute the m, okay, on the next slide, going to distribute the m here on the right side. So that's negative m x squared y cubed plus m, okay, minus 2n. So as you can see, okay, we have also here an x squared y cubed term, same as this one. So meaning these two are equal. Okay, so meaning that 3x squared y cubed on the left side is equal to the x squared y cubed on the right side. Okay, so meaning 3 here is equal to negative m. Okay, therefore m is negative 3. All right, and then for the constant part, it's 1 on the left side. Okay, meaning 1 here. So the right side na ato equate should not contain any variable. Okay, it's a pure constant. So if dili gani, in a variable involved, then you have to double check your solutions from step one maybe. Kasi na ay sayop or somewhere. Alright, so if m is negative 3, so we solve for n. So let's plug in negative 3 here and then solve for n. So that's 2n is negative 3 minus 1. Okay, or 2n is negative 4. So n is negative 2. So if we go back to the previous slide, so it's x to the m, okay, y to the n for the integrating factor. So that's x to the negative 3, y to the negative 2, okay, for the integrating factor. So we're going to multiply. So this is the third step already. So we're going to multiply the entire equation, okay, by the integrating factor. So we write the integrating factor first and then the original equation with the dx version, okay, or the differential differentials, okay, present, not the original one na y prime pa. Okay, equals 0. So that's 2y dx minus 1 dx with y cubed minus x dy. Okay, if we're going to multiply now the integrating factor, so that's 2x to the negative 3, y to the negative 1, okay, for dx, and then minus, all right, x to the 0, then y to the 1, okay, and then minus x to the negative 2, y to the negative 2, dy, okay, equals 0. So we're going to test again. That's for the next step. Okay. So the partial derivative of this new m, Okay, with respect to y, I'll write na lang the result here. Okay, these ion space. So x here is a constant. So that's 2x to the negative 3 times derivative of y to the negative 1 is negative y to the negative 2, or that's negative 2x cubed, or rather to the negative 3 y to the negative 2. And for n, partially differentiate n. Okay, so we have here a negative sign. So distribute na ha, the negative sign para I will not write many parentheses or grouping symbols. So that's plus x to the negative 2, y to the negative 2. This is from here, by the way. So if you need to write really what is m and n para dili ma-confused or what, then go ahead. Okay, so y here is a constant. So it's uh, 0 for the first term, and then for the second term, so that's negative 2x to the negative 3 for the derivative of x to the negative 2. Okay, then times y to the negative 2. So since these two are equal, okay, double check no, if correct and science. So since they are equal, so meaning this is already an exact, okay, differential equation. So we'll use that. Okay, so let's say this time I'm going to use the dy term. It's not wise to use the dy term actually for solving for f. Okay, because it has two terms and then there's a negative sign. But yun here, it's very critical. Pwede ra pod na a plus na lang yun idaan. Distribute the negative 1 before going to the succeeding steps para lesser chance na sayop, no, ang signs. Okay, so choose a more simple one. That's the next step. Okay, solve the exact PE. So let f be the integral no, of 2x to the negative 3, y to the negative 1. Okay, partially integrate this with respect to x. So y is the constant times integral of x to the negative 3. It's x to the negative 2 over negative 2. And the variable of integration, or the constant of integration rather, is y. So it's negative x to the negative 2, y to the negative 1, a plus the g of y na we need to solve for. So steady sa siya dire, ato lang nang balikan later. And then we're going to partially differentiate this with respect to x, or rather to y, sorry, not to x, kaya mo balik na sa agi, no? To y. So x is the variable, is a constant, rather. So it's negative x to negative 2 times negative y to the negative 2 for the derivative of y to the negative 1, and then plus g prime of y. And we're going to equate this to n, which is negative. Okay, so let's use this version, the one with the negative sign or the negative 1 multiplied na no, to everything here. So it's negative y plus x to the negative 2, y to the negative 2. Okay. So for the right side, if simplify it, so it's x to the negative 2, y to the negative 2. So commoning with x and y, so we are going to cancel them out. So ang mahibilin should be a pure function of y, which is negative y. So g prime y is negative y. So from the previous slide, the G prime of y is negative y. So to solve for g of y, we are going to integrate this. Okay, negative y dy. So it's negative y squared over 2. Okay, and of course with the plus c. So you can write plus c or write it for bili. Okay, and then we go back to the f equation. So the f equation um, was negative x to the negative 2, y to the negative 1, k plus g of y. So we plug in the value of g of y. So that's minus y squared k over 2. And equate this to c equals c. Okay, or if we're going to remove the negative exponents, and also the 2 in the denominator, so we multiply it by 2 times, and then I don't want the negative signs here, so we multiply by negative 2, and then we remove x to the negative 2, so we multiply it by x squared, and for y to the negative 1, multiply it by y squared. Okay, so meaning that's 2, okay, so y to the negative 1. Okay, so that's going to be y to the power of 1. Okay, for the, okay, so it should be y only and not y squared. Okay, divide na put the ani by y. Okay, so it's y to the power of negative 1 times y to the power of 1, or that's y to the 0 or 1. Okay, and then that's plus, cancel the 2, so we have x squared and y squared times y is y cubed. Okay, and then plus or equals the right side, negative 2 times c, it's just constant. Okay, so c times x squared y. So this is our final answer. So we can actually check if our solution is correct or not, but this is not required. So if we're going to check, okay, um, meaning um, we start with this expression using the exact differential equation. So this one, I'm going to use this, okay, and not the arranged one with positive exponent, because c is now multiplied to x and y expressions. So dili ma-eliminate ng arbitrary constant. So according to the definition of an exact differential equation, so this should be an exact DE. So if we're going to solve for the total differential, okay, so we're going to start with dx. Okay, so meaning we differentiate partially with respect to x. So meaning that's negative of negative 2x to the negative 3, y to the negative 1, okay, dx, and then plus for dy, okay, so that's negative x to the negative 2 times negative y to the negative 2 dy, okay, for the first term here, and then for here, it's pure y. So dy ra na siya. Okay, and derivative of y squared over 2 is just 1/2 times 2y. Okay, dy, and then right side, the derivative is 0. So it's 2x to the negative 3, y to the negative 1 dx. So the resulting equation should be the exact dE, no? Not the original equation because it's an inexact dE. So the one after multiplying the original equation with the integrating factor. Okay. So for the dy, so that's going to be plus x to the negative 2, y to the negative 2. Okay, if we are going to combine these two, so that's minus y. Okay, this is y, minus y, and multiplied to dy. So the original, or not the original, okay. So it's minus lang to here, no, for the transform equation. So it's 2x to the negative 3, y to the negative 1. This is correct. And if we just shift the negative sign, so it's negative y, and then plus x to the negative 2, y to the negative 2 equals 0. Okay, you can just go back to the previous slide, to check. So you can check, okay, if you got the correct solution, okay, by solving backward, of course. So meaning by differentiation. Okay, if it would yield to the given or the solved or the transformed equation and the exact differential equation, then your answer is of course correct. Okay, but this step is not um, required for your solutions, just for checking purposes.